In this section of notes, we're going to look at another chi-square test called the test for homogeneity. What we did in a previous section was we wanted to know, does some distribution match a claimed distribution? That's where we did goodness of fit. Here, essentially what we're doing is we want to know if two distributions are the same as each other. So the one distribution is the same as the other distribution. So this is kind of similar to what we did back in chapter 1, where we wanted to know, was there a relationship between your favorite core class and your favorite elective class? Except for that, we're just expanding it to make room for more categories, and also then to develop a test statistic and a p-value to see if those values are statistically significant or not. So here's our problem that we'll examine. We want to know whether or not playing a certain type of music at a restaurant will impact the type of entree that the customer orders. So this table gives us what kind of music was playing, what entree they ordered, and then all of the subtotals and the grand totals. So what we need to do first, if we were back in chapter 1, is we looked at all of the conditional probabilities. So given that there is no music playing, what are the probabilities that they ordered a French entree, an Italian entree, or some other entree? And then given that there was French music playing, what was the distribution? Given that there is Italian music playing, what was the distribution? And you'll remember at that time, back in chapter 1, what we did was we made bar graphs, and if there was no association, the 3 sets of bar graphs would all look the same. And then obviously we can see here that the bar graphs look different from each other, but we just don't know yet if it's statistically significant, if they're different enough. So that's where we're going to add to this and come up with something new. So again, we're doing this test for homogeneity, and our null hypothesis will be that there's no difference in the two distributions, and the alternative will be that there is a difference in the distribution. So what we want to do is we want to use our proportionalities to come up with expected counts. So we're going to keep all of the totals and subtotals the same, and then we're going to use proportions to figure out what the expected count should be. So for example, the 30 people that had no music and then ordered a French entree. Theoretically, if we're using proportions, what we're going to do is we're going to take the row total, so the French total, which is 99, and then the type of music total, the none column, which would be 84, and then divide by the table total, which is the 243, and then that would give us that if these were really evenly distributed, that our expected count would be about 34.22 people that listened to no music and then ordered a French entree. So we can see that that expected value is a little bit higher than the actual value that happened, those 30 people. So if we repeat that, that's going to give us each entry in the table, each expected count. We do the row total times the column total divided by the table total. Now in terms of our conditions to do the test, these should look familiar, although there is one small difference. So we do still want there to either be a random sample or random assignment, depending if we're talking about a study or an experiment. If we're doing a study and we're taking a sample without replacement, we're checking the 10% condition, just like we have in our previous tests. But what's different is our large counts condition. So our large counts condition, if that's met, that's what's going to allow us to use the chi-square distribution. And in order for that to work, we need to have expected counts for every value in the table. Every time we did a row total times column total divided by table total, all of those numbers need to be larger than 5. So if I were to repeat that process, we already got the 34.22 for the people that did not listen to any music and then ordered French. If we continued that for the other entries, this is what we would end up with. So we have 9 entries for the type of music and the type of entree ordered. And we're going to use the same formula for our chi-squared test statistic that we did for goodness of fit. where we do the observed value minus the expected value, square it, and then divide by the expected value. So if I just start with the people that listened to no music and then ordered French entrees, that part of my chi-squared test statistic is the 0.52. And then I would do that for all 9 of those values, add them all up, and that gives me an overall chi-squared test statistic of 18.28. So now that we have a test statistic, we can get our p-value. Remember that you can either use your table or you can use your calculator. So if we're going to use our table, then we need a degree of freedom formula. And our formula for degrees of freedom for our homogeneity test is the number of rows minus 1 times the number of columns minus 1. So in our problem, there were 3 types of music, either no music, French music, or Italian music. And then there were 3 types of entrees, either French, Italian, or neither. So there's 3 rows and there's 3 columns. So 3 minus 1, 3 minus 1, multiply those together. That gives you your degrees of freedom. So that tells us which row we should look in if we've decided to use the table. So if we've decided to use our table, we're looking at our row for degrees of freedom, so 4, and then we're trying to find something close to our test statistic inside of that table, and then we're getting as close as we can. So our test statistic was the 18.28, and that's closest to 16.42 and 18.47. So that tells us our p-value is somewhere between 0.0025 and 0.01. Now, if we wanted to use our calculator, we can use our chi-squared CDF, where you give the lower bound, comma, upper bound, comma, degrees of freedom, and that will give you a more exact answer. Now, there's also a way to take your observed counts table and put that into a matrix in your calculator, and it will do all of this work for you. There'll be a separate video on that, so make sure you do try that before you move on to the practice problems. Now, this next part, when we come up with our conclusions, this is pretty similar. So remember, your p-value gives the probability of getting the test statistic that you got, or even more extreme, purely by chance. So that means there's a 0.0011 probability observing a distribution that is as different as ours was, or even more, purely by chance, assuming that the fact that there is a certain kind of music playing didn't make a difference on the type of food ordered. And then in terms of your conclusion, remember, you still take your p-value and you compare it to an alpha value. So 0.0011, that's less than 0.05. That means we can reject the null hypothesis, and we have convincing evidence for the alternative, which is that the distribution of entree ordered is different based on the type of music being played. And then what's even more interesting here is that we did random assignment, so that lets us make a cause and effect statement. So we can say that the difference in music is what caused the difference in the type of entree ordered. Now, you might recall from when we did our goodness of fit tests, each of the parts of the distribution, I think we did colors of M&Ms. So we said each color had a contribution towards the distribution and how much it impacted the chi-squared test statistic. We have a similar thing here. So what I've given you here is some computer output, although this would be similar to your calculator output if you were going to use matrices as well. And what we're looking for is each of these values here that we've boxed. So you can see the parts that I highlighted in yellow, those were our observed counts, and then those green parts should look familiar. Those were our expected counts. And we're looking for the ones that had the largest contribution. So out of the things that were green, those ones that are highlighted or in the red box, those are the largest values. So we say that those are the largest contributors